Hello everyone. Welcome to this video on section 2.3 called Volumes of Revolution, Cylindrical Shells. In this video, I'm going to be taking you through a sample version of the Newton-Alta assignment for this section. Please understand that the questions I see in this video may not be the same questions you see if you're working on the same assignment. You may see different numbers or different functions, but the types of problems will be similar enough that I'm hoping watching me do these here will help you out when you're working on them on your own. All right. So here is the Newton-Alta assignment, at least a preview of it, right? You won't see the word preview. For section 2.3, you got the title of the assignment on the top left, the mastery bar, right, telling you how far along you've gotten in the top right, activity log, telling you how far you've gotten in each objective. Right, so it looks like there are 3 objectives for this particular assignment. And then you have a question related to a current objective. And at the bottom of every question, you should be seeing a feedback button. All right, so if you ever see any typographical errors or issues with the question that you're seeing, you can send feedback directly to Newton. You will not have this instructor cheat button, right? This is instructors only. But you will have a more instruction button. So if you're ever struggling with a particular objective or a question, hit this more instruction button and you'll be taken to another page, a separate area called more instruction, where you'll be given some videos to watch or reading to do or both. And then along with that, some other questions, related to that objective. And you can work on those questions with the instructions still up on the screen for you to look back upon. And perhaps that will help you get through the assignment. All right. So now, the first question I'm seeing, the objective here is calculate the volume of a solid of revolution by using the method of cylindrical shells. All right, so if you recall, if you saw section 2.2 from this Newton-Alta Calculus 2 assignment pack, we did volumes of revolution, right? Solids of revolution, where you take a region on the XY plane and then you revolve it or rotate it around the x-axis, the y-axis, or some other horizontal line or vertical line. And that rotation creates a 3-dimensional figure. And you're trying to find the volume of that figure. In section 2.2, we use the disk and or washer method, where I would take slices of the region, it's a tiny thin little rectangle that was perpendicular to the line we were rotating across, right? If you want to create a disk or a washer, you take little thin strips, thin slices perpendicular to the line you're rotating around. But if you want to get these what are called cylindrical shells, you need to take your little thin strips of the region or thin rectangles, thin slices. You need to take these thin slices that are parallel to the line of rotation or the axis of rotation. All right, so I'll describe that out when we actually write out this first problem on a piece of paper. So in this first question, right, the region R is bounded above by the graph of f of x equals 2x to the 2/5 power, and below by the x-axis over the interval from, x equals 0 to x equals 5. So I will draw this region on the xy plane, and then we're going to find the volume of the solid of revolution formed by revolving this region around the y-axis. Okay, so here I am, some piece of paper. So I'm going to draw this region as best I can on the XY plane. And they said we're over the interval from x equals 0 to x equals 5, right? So I'll throw 5 over here. And the function we were given was, f of x or y equals 2 times x to the 2/5 power. And if I plug in 0 for that, I'm getting 0, so that has the origin on it. If I plug in 5 for this, that'd be 5 to the 2/5 power. Right? I mean, it's the fifth root of 5, squared. It's some positive numbers. I'll just put it up here. I don't know. I could go to a calculator if you want, but we have 2 times and then 5 to the 2/5 power. I just know that's going to be positive somehow. And then the graph of this curve, right? This is x to a power less than 1, right? So remember, square root of x, cube root of x, your x to the power less than 1 is a concave down curve to the right of 0. So it looks something like that. Just that little piece of it over the interval from 0 to 5. And so this region being talked about here, right? This region R is, down to the x-axis here over the interval from 0 to 5 is this region here, right? So here's region R. So that's the region being described. Now we're asked to revolve this region or rotate this region around the y-axis. So I'm going to make this little loop here. Rotate around the y-axis. Now, hopefully you can picture that if I were to sweep this around the y-axis, I'd create a little three-dimensional shape with a little divot in it, kind of a bundt cake. If I do this, right, we create a 3D figure. I'll just say a 3D figure, and it will look something like this. You'd have this on the inside, across the reflect across the y-axis. You got that, got the edge of it over here, and then it's it'd be circular. It has these circular, well, actually more like a washer cross sections if you're going horizontally, and it's going in like this, right? It's got a divot. It's got a little. It's like a cylinder with a tornado cut out of it. Right? Add some more crap to it, but it's like a cylinder with some tornado cut out of it. Some little like funnel shape cut out of it. And what we're asked to do is, right, is we're asked to find the volume of this shape, of this 3D figure. Now, as I mentioned, last section, section 2.2, with the disk and washer method, we would take slices of our region, little thin rectangle strip, that were perpendicular to the line of rotation. But to create these cylindrical shells, what they're calling, and I'll draw a picture of one here in a second, but for a cylindrical shell, we're going to slice parallel, take little thin rectangular strips parallel to the axis of rotation or the line of rotation, line of revolution, whatever you want to call it. So we're going to make slices parallel to the axis of rotation. So if I do that here, now if I do parallel to the y-axis, that's a vertical strip. Right out here, so say here's one little slice, and that would be that would be above some particular x value from 0 to 5 here. So I make this slice of the region, right? Think about it as some thin little rectangular strip, right? Very thin rectangle. The thickness of this rectangle is some little change in the x value, right? Some little change, horizontal change, which you could call delta x. But because we're going to have delta x approach 0, that'll become infinitesimally small, right? So I'm just going to call the thickness of this straight up, dx. Now, if I take this slice and rotate the slice, or revolve the slice, this little rectangle, around the y-axis, and what's being created here is going to be called a cylindrical shell. And it really is just like a rolled up piece of paper. I know this might not be super visible to you, but here's a piece of paper. Yeah. And you can imagine my thin rectangle is like this thin little edge. All right, looking at it from above here, just a thin rectangle, vertical, thin piece of a thin rectangle, thin slice. And then I roll this up into a circle, right? I rotate it around some line, and it would sweep out a shape, when it connects to the other side here, sweeps out a shape that is just a rolled up piece of paper. Right? Just a rolled up piece. So a rolled up piece of paper is an example of one of these cylindrical shells. Now I'll also draw a picture of this. So I have this, the height of the shell will be just the height of my rectangle here, right? So the height of the shell, I'll call this height here, right? The height of the shell. And then again, I'm rolling this around the y-axis, so I create this like cylinder shape. Right? And again, it's very, very thin. Okay, so I got this little thin ring with a big gap in it, right? It's just a rolled up piece of paper where down the center of it is the y-axis, right? The axis of rotation. All right. And the thickness of this ring, right, is just the thickness of our piece of paper, the thickness of this rectangle slice, right? So thickness is dx here. All right, so the shell has a height, which is in my picture up here of the region. This should be the height of the shell, right? It's just the height of the rectangle. And then it involves a circle somehow, right? This would be circular, right? You rotate it, it's a rolled up piece of paper, a circular rolled up piece of paper, a circular base. It's like, again, it's a circular cylinder. And you also have a radius, right? So the distance from the axis of rotation to the rectangle itself, right? You also have a radius. So I'm going to call the height h and the radius r, okay? And on my picture, right, you got the height of the on the picture of the region, the height of the rectangle is the height of the shell, h, and then this radius I'm going to look for is the distance from the axis of rotation to the rectangle. So that's radius of the shell, which again I called r, right? And what I would like this height and this radius in terms of x, because I have dx as the thickness, right? We're going to be integrating with respect to x, so I want everything in terms of x, but we'll get to that later. For right now, what I want to do is say, hey, what's the volume of a cylindrical shell? One of these shells. So the volume of a shell, think about remember I said earlier, this is like a rolled up piece of paper. let's think about unrolling the shell into a sheet of paper. So you have this picture here, like this. Just a thin sheet of paper. Again, very thin. I'm not the greatest artist, I'm sorry. It's better. Yeah, very thin. So again, the thickness of this piece of paper called dx, right? Now, hopefully you can see if I unroll this. The top edge, right? I'll color this in like red. The top edge, the length of this top edge here on this piece of paper, this thick, this is like a rectangular prism here. The top edge here is the top edge here, right? It's the circumference of the circle. So this top edge here is the circumference of my ring, the circumference of that rolled up piece of paper, that cylindrical shell. I'll just write circumference. And remember, circumference of the circle with a radius of r is 2 pi r. And then, of course, this length here, right, that's the top edge, and then this edge here is this edge here, right, when you unroll it. It's just the height of the shell, which again I was calling h earlier. So the volume of a shell, let's call it V shell. The volume of a shell is just the volume of this little piece of paper, this thin rectangular prism. It's length times width times thickness. It's the area of one face times how thick it is, which would be, the circumference of the circle, right? The circumference of the ring times the height, so 2 pi r times h, that would give me the area of this one face, and then times the thickness, dx, and, in other problems we'll see it with dy. And as I mentioned earlier, now what I want to do is get r and h in terms of x, right? If this thickness is dx, I should get the r and h in terms of x. Okay, so for this particular example, see the radius here is just from the y-axis, from x equals 0 to the x value I made my slice at. So that's just x units. That's just straight up right x units. So the radius is x when you write it in terms of x. Whatever I picked for x here to make my slice, that's going to be the radius of the shell. So 2 pi x. And then you see the height is just the height of this rectangle, the height of the shell. And the height is the y coordinate of this point on top here, minus the y coordinate on bottom, but the y coordinate on bottom is 0. So it's just whatever the y coordinate is up here in terms of x, but any point on this curve, we saw the y coordinate is, 2 times x to the 2/5 power. So the h for any value, when I make a slice at a value of x, the height of that slice, the height of that thin rectangle will be 2 times x to the 2/5 power. So circumference of the ring, 2 pi x, 2 pi times the radius, times the height of the shell, the height of the rectangle, 2 times x to the 2/5 power. And then times the thickness, which is, dx. So there's the volume of a single shell. And what I would like to do now is make a shell for every x value here from 0 to 5. And when I create all those, we'll get a bunch of pieces of paper put inside each other, to form, rolled up and put inside each other to form this 3D shape. And that'll give us our volume. So the total volume of our three-dimensional figure is going to be the integral from, right, we did this from x equals 0 to x equals 5. Right, we would do this for every x value from 0 to 5 of these shell volumes, right? I'm adding up all these shells volumes together. Now, notice this 2 pi here times 2 here, that's 4 pi. I'm going to pull 4 pi out, right? That's a constant multiple. simple constant multiples out of integrals. And then x to the first times x to the 2/5, that'd be x to the 7/5, right? One is the same as 5/5. And 5/5 plus 2/5 is 7/5. And then that takes care of all that. And then you got times the thickness, right? Times dx. Okay. And this is a simple power rule thing. I can integrate this pretty easily, right? This would be 4 pi times, and then, the antiderivative of x to the 7/5. That'd be x to the 12/5. And then, because you're adding 5 over 5, and then times 5/12. And we're evaluating this from x equals 0, x equals 5. And I could pull the 5/12 out of this, right? Again, another constant multiple here. So this is actually, 4 goes into 12 3 times. So this is 5 pi over 3 out here times, and then if I remove the 5/12, now I'm just evaluating x to the 12/5 at 5 and 0 and then subtracting. So it'd be 5 to the 12/5 minus 0 to the 12/5. Well, 0 to the 12/5 would be 0. So I just get here 5 to the 12/5 power. And if I multiply by another 5, if I want, this would be pi over 3 times 5 to the, this is 5 to the first. Add that on that. That is 5 to the 17/5 power. And I'm pretty sure that they're going to be taking this. This is perfect. All right. And that's cubic units, right? Units cubed. Pi over 3 times 5 to the 17/5 power. Now you could write this as something with a fifth root and junk, right? Actually, this is 3 and 2/5. So I could also write this as pi over 3 times, then 5 to the third is 125. And then 5 to the 2/5, I could write that as the fifth root of 25, They might write it that, 125 pi over 3 times the fifth root of 25. They might write that as well. Same value, right? Same value. All right, and that's what I'll be entering. Let's check it out. I go back here. So I have pi over 3 times, and then 5 raised to the 17/5 power. Oops, down there. And that should be good. Great. Yeah. See, they have 125 times, remember I said the 125 times the square root of 25, that's 5 to the 2/5 pi over 3. Same thing, right? As long as you're entering a value that's equivalent to the correct value, they should give it to you. All right, and then after every question, right, you have some sort of answer explanation. I would highly recommend reading these, whether you get it right or wrong. If you get it right, perhaps they did it a different way or a way that you like better that you might want to try for future questions. Obviously, if you got it wrong, read through the answer explanation and see if you can figure out where you went wrong. And a nice thing here too is you can see the 3D figure that they're showing, right? So here's the region that we had, right? There was the graph of f equals 2 times x to the 2/5 between 0 and 5, right there to the x-axis. There was the region I drew on my paper. And then they rotate this around the y-axis and they have you kind of do it, right? So let's see what happens. I move this little dot here, see what happens. Yeah, if I rotate that region around the y-axis, see, I start creating this three-dimensional shape. Right. Like I was saying earlier, and you can move this up and down, take a look at it from all sorts of angles. It kind of dips in like a tornado down here, right? Closer, and you see how it's curling in like this, and it's like a little vortex here. And then this red, right? The green is the whole shape, and the red here is one of the cylindrical shells. It's got a height that's just to our curve, and the thickness is really thin, right? It's really thin It's just a thin rolled up piece of paper, this red shell here. Right. Yeah, so they give you just an idea as to what the thing that you're actually finding the volume of looks like, which is nice. Okay, great. And that's the method of cylindrical shells, right? You're making a slice parallel to the line of rotation, the axis of rotation, to create these shells rather than perpendicular, right? Perpendicular made discs or washers. Okay, next question. So we're in a different objective. So last time we had everything in terms of x, we're probably going to have everything in terms of y here. As it says, calculate the volume of a solid of revolution by using the method of cylindrical shells for functions of y. So again, we're described some region on the xy plane, bounded on the right by u of y or x equals y to the 3/4 power, and on the left by the y-axis, and we're only looking between y equals 0 and y equals 4. Find the volume of the solid of revolution formed by revolving this region around the x-axis. Okay. So just like the last example, going to draw this region they're describing. So we were going from y equals 0 to, between y equals 0 and y equals 4. The curve we were given was u of y or x, right? U of y, x, same thing. X equals y to the 3/4, right? And this was the curve on the right. The curve on the left is supposed to be the y-axis. Now, if y were 0, x would be 0. So 0, 0 on this. And if y were 4, you get the fourth root of 4, the fourth root of, 64, which is some positive number for x, all right? So I'm just going to do this here, right? Here's 4 to the 3/4 power, right? Some positive value. You have that. And this would be y equals x to the 4/3, right? Some power bigger than 1, so it'll be a concave up. So here's and there's just some curve over here on the right, right? There's your curve. Just between x equals 0 and x equals 4 to the y-axis here on the left. So here's the region, they were calling it region Q. So that was region Q. And we're asked to revolve this region around the x-axis. So this would be pretty similar looking to the last shape, right? I'm not going to draw it because, again, I'm not great at drawing the 3D stuff, but when I rotate this around, it'll be like a cylinder with a little funnel cut out, right? A little tornado cut out of the middle. And we're trying to find the volume of this bundt cake shape, right? This divoted cylinder. Right. So if I want to produce, discs or washers, I make slices perpendicular to the x-axis. But I don't want to do that. We're asked to do cylindrical shells. So again, I make a horizontal slice. I make a slice, right? Think of some thin rectangle in the region that's parallel to the line we're rotating across, parallel to the x-axis. And any horizontal line or any horizontal segment corresponds to some y coordinate, some y value, between 0 and 4, of course. And when I rotate this slice, right, now the thickness of this slice we'll call dy, right? It'll be some tiny change in the y-axis, tiny vertical change. And when I, rotate just this rectangle, just this little slice around the x-axis, we get a shell. Some thin piece of paper rolled up. Right, very thin. Imagine that's really thin. Right? And in the middle, right, going through the center of the hole in the middle here, the hollow part, there is the axis of rotation, right? The line we rotate around. And the thickness is, dy, right? The thickness is dy. I want the radius, and I want the height, right? I'll call this the height, even though it's not up and down. Right? Now, as with the last example, right? This height is just the length, or here the width of my rectangle in the picture of the region. And then the radius of this ring is the distance from the line we rotated across to the rectangle, right, to my slice. Now that distance is simply whatever y value I made the slice at. So the radius is simply y. Right, I want everything in terms of y. We have a dy here. And then this height, right, this distance across here, that's the x coordinate of this point on the end of the rectangle. But the x coordinate of points on this curve in terms of y are, is y to the 3/4, right? So y to the 3/4 for the height, the distance across that rectangle. And that would be the height of the shell. Okay, so the volume of one shell, right? This is a cylindrical shell. The volume of a shell is going to be the circumference of the ring. So 2 times pi times the radius. But the radius we said was just y, if we're writing everything in terms of y, times the height of the shell, which we said here was the length of this rectangle, which in terms of y is y to the 3/4, and then times the thickness, right, times dy. And I'd be doing this, right, finding the volumes of these shells and then adding them up for every y value in this region, which would be from 0 to 4. Okay, so the total volume of the figure, the 3D shape that's being created, is going to be an integral from 0 to 4 of these volume of the shell volumes. Now there's 2 pi as a constant multiple, right? So I'm going to pull that out. We got 2 pi. And then y times y to the 3/4, right? That's y to the 7/4. 1 plus 3/4 would be 7/4. And then times the thickness, right? dy. And yet again, this is something I can just apply a simple power rule to take the antiderivative. So this is 2 pi times, and then y to the 7/4, right? I would add 4/4, make that y to the 11/4, and then times 4/11, right? Times the reciprocal of the new power, and that's it. And there's only this one constant multiple here. I can pull that out. We're going from y equals 0 to y equals 4. Pull out the 4/11, that's 8 pi over 11 multiplied by, and again, I pulled out the 4/11, right? So I'm going to cover that up. And then I would just have 4 to the 11/4 minus 0 to the 11/4, right? So just 4 to the 11/4, right? Times 4 to the 11/4. And this should be good. Now you could simplify this a little more. This is 2 squared to the 11/4, so 2 to the 11 halves. And this is 2 to the 3, so 2 to the 6 halves. That'd be 2 to the 17 halves times pi over 11. But this should be good as well. But I'll write that though. Pi over 11 times, 2 to the 17 halves, which is 8.5 and whatever. There's a lot of equivalent values I could call this, or I could do all sorts of weird simplification. But I'll type this one in. All right, you could type this one in too, but whatever. That's the volume of the three-dimensional shape that would be created by rotating that region around the x-axis. So let's go to the volume assignment here. I have pi over 11 multiplied by 2 to the 17 halves power. I'm just double checking that I made that's 11 halves plus 6 halves. Yes. All right. Right. And so they actually wrote it out, 2 to the 17 halves. That'd be 2 to the 8th times 2 to the half, and 2 to the 8th is 256. So that's 256 times the square root of 2 times power over 11, right? So they got that there. All right. And again, here's the region we were shown that I drew, right? And then rotate that region around the x-axis, and you can see the 3D shape being formed. I'll do it slowly. And and again, that little the red thing there is one of the just one of the cylindrical shells that would make up the whole green shape, right? And the volume, and then the rest of it is, we found the volume of that green figure. Great. All right, so here's another one for functions of y. I'm doing the same thing every time. Now this one, notice multiple choice. We're just setting up the integral. All right, what integral would end up giving me the volume of the solid of revolution that's formed by rotating some region? About this time, right, the region is being rotated not about the x-axis or y-axis, but about a different horizontal line, right? Y equals -1/2. So once again, I'll draw the picture of the region. I'm not going to draw the shell though, right, this time. Let's just save some time. But we can still look at the picture of the region and one of our slices, one of the thin rectangles, and deduce what the radius and height of a shell would be. Okay, so XY axis here. So this region is bounded by the line, one curve they give us is x equals 5. All right, so that's just a vertical line. I'll draw that in a second. Another curve they're giving us is v of y, which is x. All right, some input y, output x. X equals 5 times the square root of y. All right, and the x-axis, right, and the x-axis is also being bounding this here. And that's it. Okay, so now x equals 5 root y, right? When y is 0, x would be 0. Um, and when x is 5, right? When x is 5, y would have to be 1, right? It's 5 times the square root of 1 would be 5, and there's that for 5, 1. So there's x equals 5, vertical line. I guess I should have drawn that in a different color, but there's x equals 5. And then x equals, 5 root y. This would be the same thing as y equals x squared over 25. So it's some parabola opening up like this, or this part of that. And also the x-axis. There's our region. Still checking here. Y equals x squared over 25. Yeah. Okay, so here's the region in question. And once again, they were calling this region, Q. And we are asked to rotate Q, not about the x-axis or the y-axis, but about the line y equals -1/2. So let's say that's here, right? There's -1/2 on the y-axis. Y equals -1/2 is this line. I'll tell you this here. When you're rotating around a line that's not the x-axis or the y-axis, but some other horizontal line or some other vertical line, all that's going to change is the radius of the shell. By here, it's going to change by either a half or -1/2. It'll be increased by a half, or you might have half minus something, but it'll involve a half somehow. So watch, right? So if I'm doing cylindrical shells, it means I'm going to take a slice of this region. So again, that's parallel to this line. So a horizontal slice. So let's say that here's a slice, a thin rectangle with a thickness of dy, right? And this would correspond to some y coordinate here between 0 and 1. And then if, again, I'm not going to draw the shells too much anymore. But if I were to revolve this rectangle, this thin rectangle around the line y equals -½ I'd get a rolled up piece of paper. I'd get this thin ringed cylindrical shell. And the radius of the shell and it's the distance from the line to the rectangle, right, to the edge of the paper. So there's the radius of the shell, which I'll get in terms of y, right, because I got dy there. And then the height of the shell is, this distance here. It's the length of the rectangle from here to here. Okay. The radius, simple enough. See how it's normally we were going from the x-axis or from the y-axis. If I go from the x-axis to this point here, that's the y coordinate. So that's y. That's just the y coordinate of that I chose, the y value that I chose for this slice. And then we got to add to that, half a unit, right? Because this line here is half a unit further from the x-axis. So the radius, when all is said and done here, the distance from this line to that rectangle is y, whatever y I chose, plus a half. So not just y. Right, now this height, right, the width of the rectangle here, that's that's the x coordinate to the right curve minus the x coordinate to the left curve. Now the x coordinate on the right curve is 5, so that's 5 units. I take away this much, and I'll have what's left over is the length of the rectangle there, the width of the rectangle. And this x coordinate, I'm on this curve here, is 5 times square root of y. So 5 minus 5 times square root of y. And there's the height of the shell, right? When I rotate this rectangle around the line y equals -2 and create a shell, this will be the height of that shell at whatever y value I pick. All right, so the volume of one shell will be 2 pi r, the circumference of the ring, times the height, and then times the thickness. And we'll be doing that shell work for every y coordinate from 0 to 1, right? So the total volume, I'll just skip to the total volume now. We'll be integrating from y equals 0 to y equals 1 of these shell volumes, right? Again, which will be the circumference of the ring, so 2 pi, you can pull the 2 pi out if you want, times the radius, right? And we saw the radius here in terms of y was y plus a half. And then times the height, right? Circumference of the ring times the height of it, which is the length of the rectangle here, which is 5 minus 5 square root of y in terms of y, and then times the thickness, right, times dy. And this is it. This is all they asked us to do here. We could go about, actually multiplying this out and integrating and whatnot, but I'm not gonna, because all they wanted was you to set up the integral. Right, so if I look back here, the only one of these that actually looks like what I wrote is this one here on the bottom. All right, 2 pi times the radius was y plus a half. The height was 5 minus 5 square root of y. Thickness dy, integral from y equals 0 to y equals 1. That integral should lead me to the volume of the shape created. And once again, they've got a picture of the region. All right, this was our region. And then what happens when I rotate around the line y, see a little dotted line down here, that's where y equals -½ is. I rotate that region around, and you're going to get this three-dimensional shape, and it'll actually have a nice gap in it, right? If you look at it this way, it's got a hole in it, right? Because there was a gap between the region and the line you rotated around. So you got this like almost like a little funnel shape created here. And once again, this little red region is just one of the cylindrical shells created when rotating a thin rectangle around the line y equals -half. Okay, great. So again, that's half the battle there. That's most of the battle, actually, I'd say, was setting up the integral, right, to find the volume, because then hopefully the functions are nice enough to where your integration afterwards is relatively simple. All right, so let's move on. All right, so another cylindrical shells problem. Notice here again, we're taking our region, whatever this region described is, I'll draw it out, and rotating the region about a line that's, x equals 2. That's a vertical line. Notice it's not the x or y axis. So what's going to happen is the radius will change by 2 units somehow. It'll involve a distance from 2 units somehow. All right, +2, -2, 2 -2 plus. All right, it'll involve some adding or subtracting from the number 2. And just like the last question, right, they just want us to set up the integral that would lead us to the volume of the shape created. So let me draw that picture. Draw the region. So their curves they're giving us says region R is bounded by the graphs, f of x or y equals the square root of x, g of x or y equals, x squared. And we're on the interval from x equals 0 to x equals 1. And both of these would have the point 1, 1 on it. And, square root of x would be like this. That's square root of x. And then y equals x squared would be like this, curving up. Right? And therefore, the region we're talking about here is this region, right? So here's R, right? What they were calling region R. And we're rotating this region around the line x equals 2, right? So here's x is 2, and I'm going to make a little dotted vertical line here. Here's x equals 2, and I'm rotating around this and creating some 3D shape with a big hole in it. And we're trying to find the volume of this 3D shape. So once again, if I want to do shells, right, shells, I need to make a slice, make a thin rectangle in my region here that's parallel to this vertical line. So I make a vertical slice. So here's some vertical slice, right, again, some thin rectangle. And that would correspond to some x coordinate, right, some x value between 0 and 1. And my thickness is dx, and imagine, I'm not going to draw it, but imagine, right, I take the thin rectangle, rotate it around this line, I'd create one of these rolled up pieces of paper, right, one of these cylindrical shells. Right, so again, the radius of the shell, the radius of the circle, right, for the top of the and bottom of the shell is this distance here, right? It's always the distance from the line of rotation to my slice, to my rectangle. And then the height of the shell is just the height of the rectangle. Right? And I want both of these in terms of x, right? Now I have dx. So I'll get both of these in terms of x. Okay, well, the radius, right, for the radius, take a different color here. See if this shows up. See, normally I would go from the y-axis, right? So this distance here to my rectangle Isn't that's just the x coordinate I chose, right? This distance is just x. But what we have is, to the line, that's 2 units all the way across. So then this distance here, right, would be 2 minus x, right? It's the whole thing of 2, and then taking away that x, and I'm left with what's left over, which is my distance that I want from the line to the rectangle. So 2 minus x is the radius in terms of x. And then the height at this x value is, the y coordinate to the top curve minus the y coordinate to the bottom curve. It's the y to the top minus the y to the bottom, which in terms of x, the y on top is square root of x, the y on bottom is x squared. So you have square root of x minus x squared for the height of that rectangle, which would be the height of the shell, when I rotate that around the x-axis and create a shell. Okay, and then I'd be doing this for every single x value, creating these shells and adding up their volumes, from x equals 0 to 1. All right, so the total volume of our three-dimensional figure that would be created would be the integral from 0 to 1, to 0 to 1, of the volumes of these shells. And remember, I said it before, the volume of a shell is the circumference of the shell, right? So 2 pi times our radius, which I said in terms of x was 2 minus x, times the height of the shell, the height of the rectangle, square root of x minus x, when I got that in terms of x, square root of x minus x squared, sorry, and then times the thickness of the shell, right, which is the dx here, the thickness of the rectangle. And this, right, this is all they're asking us for. Just set up the integral. That would yield the volume of the three-dimensional shape. So I'm going back here and just choosing the correct answer here. And it looks like the second choice from the top, 2 pi and then 2 minus x was the radius, square root of x minus x squared was the height, dx the thickness, integral from 0 to 1. Right, that should be it. And once again, as for all these problems, right, they show you the region, right? This was the region. And they show you what happens when you rotate it around. This dotted line here is at x equals 2, right? X equals 2. And let's see it rotated around, right? You see it start creating this three-dimensional figure. And you can move this around here, see more of it. A little bowl shape, kind of with a hole cut out. And then, set up the integral to find the volume of that shape, which we just did. All right, next question. All right, so I'm back to the objective with the functions of y here. So just like all the other problems, I'm going to draw a region. I'm going to rotate that region around some line to create a three-dimensional shape and use shells to find its volume. And this time they actually want the volume, right? So I'll actually have to integrate. And if the integral ends up being a nice one, I'll just put it in Desmos. I'll put it in a calculator and let it do it for me. If I know it'll end up being a nice rational number, right? If it ends up being some irrational number, I'm gonna have to do it myself, like some previous integrals. All right. So this example here, okay, the region in question. Q is the region bounded by the graph of v of y, which is x, right? Some x coordinate equals 6y. So x equals 6y, y equals x over 6, right? It's just some line. X equals 2, x equals 0, and that's it. All right. So we're going from x equals 0, x equals 2 here, and x equals 6y. Um, when x is 0, y would have to be 0. And when x is 2, y would have to be a third. You have to point to 1/3 on this. Oh, and y equals 0. Sorry, I'm sorry. It's x equals 2 and y equals 0. My apologies. So y equals 0, that's the x-axis. right? X equals 2 is this vertical line, x equals 2, right? So there's y equals 0. Here's x equals 2, the part of it that, so we still have the point 2 for x, 1/3 for y. I mean, it's still the correct point. And then this line is just connecting these 2 points, right? So we're looking at this triangle shape, right? Here's region R, right? There's the region R in that triangle shape. And we're rotating around the x-axis, right? Rotating around the x-axis. All right, now you might remember that, if you rotate a triangle that's touching the axis of revolution around it, you're going to create a cone, right? The 3D shape created here would be a cone. And remember the volume of a cone, this is something we could do without an integral. I'll still set up an integral, but I'd get a nice cone here. And the volume of a cone is 1/3 the area of the base, which would be pi r squared. It has a circular base, and then times the height of it. And here, the radius is of the whole cone would be 1/3, right? From the middle to the edge, right? Would be 1/3. So you have 1/3 squared here for the radius. And the height of it is just, it's from the base to the tip. So 2 units. So I should end up with, this is 1/9, 1/27, 2/27 pi cubic units. So that's what I should end up with. Let's see if that happens, when we go through and set up our integral. I still want to try these shells just to keep getting the hang of them. So I'm rotating around the x-axis, right? If I want to create shells, I'm going to take a horizontal slice. Take a slice of the region, a thin rectangle, like that. That's parallel to our axis of rotation. And this corresponds to some y coordinate, right? And some y value between 0 and 1/3. And it has a thickness, say, of dy, right? Some little vertical change. Again, the radius here, right? When I rotate this rectangle around the x-axis, I'll create a shell, right? One of those rolled up pieces of paper. There's the radius, and then remember the height is just the width of the rectangle here, the length of the rectangle. And I want both of these in terms of y. Now the radius is simply whatever y value I chose, and the height is, the x to the right curve minus the x to the left curve, but in terms of y. So 2 minus 6y. That would be the x coordinate to the right curve minus the x coordinate to the left curve to leave what's left over, which is this rectangle, the rectangle length. So the total volume, right, I'd be doing this for every y value from 0 to 1/3. So the total volume would be the integral from 0 to 1/3 of, and then the volumes of each of these shells, right? The shells that are created by rotating these thin rectangles around the x-axis. That'd be the circumference. Again, I'm pulling 2 pi out. 2 pi times the radius, but the radius is just called y, right? When I write it in terms of y, times the height, right? Times 2 minus 6y, and then times the thickness, dy. And then this here is just a nice polynomial. I'm going to factor a 2 out as well. So this would be 4 pi, and I factor a 2 out, times the integral from 0 to 1/3, and this would be 1 minus 3y, and then when I distribute the y minus 3y squared, right, and then dy, and this integral should be pretty easy to take. This is 4 pi, and then the antiderivative of this would be half y squared, and then minus y cubed, and we're going from, y equals 0, y equals 1/3. Really all I need to do then is plug in 1/3 to this, because when I plug in 0, it's nothing. So that's just 4 pi times, and then half of 1/3 squared, that's half of 1/9, that's 1/18. And then minus, and then 1/3 cubed is 1/27. Right. And then this is 3/54, this is 2/54. This would be 4 pi over 54, right? 3/54 minus 2/54 would be 1/54. and divide each of these by 2, and you got what I got earlier when I said I recognized that it was just going to be a cone. 2 pi over 27. So 2 pi over 27 cubic units for the volume of this cone that would be created when you rotate this whole region across the y-axis, around the y-axis. So the volume here, 2 pi over 157 cubic units. Right, and you can see the cone, right? Here's the triangle shape that we drew, right? And then rotate it around the x-axis and you're going to see a cone forming. I'll zoom this in, move this around, right? You can hopefully see the cone shape, that green shape there. Right, nice cone shape. And the volume of that cone, of course, we found was 2 pi over 27 cubic units. Right. All right, so once again, we're simply asked to find the integral, right? Set up the integral that would help us find the volume of the solid of revolution. All right, so again, I'm going to draw the region described on the XY plane, and we're gonna, imagine, right? I'll make a thin slice, a little rectangular slice of the region, and rotate that slice around the x-axis here, right? This is about the x-axis, and get the volume of a shell and integrate from, looks like y equals 0 to y equals 4 are going to be our limits of integration. All right, let's see. So, all right, so the curves that form this region, that bound this region, we have u of y, or just x, equals negative 1/2 y squared times y minus 4. The y-axis, and then y equals 0 and y equals 4. Between y equals 0 and y equals 4. So between y equals 0 and y equals 4. Now at both of those, right, y equals 0 and y equals 4, the x coordinate 0. So you have 0, 0, you get 4, 0. And, this is like some sort of cubic polynomial. X equals, negative 1/2 y cubed plus 2y squared. And, yeah, so if you imagine, if it was y equals, if y and x were switched, it would look like this, and then I switch x and y, flip that around. It would have, 0 and 4. Like, yeah, if it were y and x, it would have 0, 0, 4, 0, and look something like this because of that negative lead coefficient. And then we're rotating this around the line y equals x. All right, switching y and x here. So move all these points up here, move all these points down here. So, yeah, so we got something over here. This isn't the greatest, but all these points in the third quadrant move up here to where I want, right? All these points with negative y coordinates and x coordinates big. These points would move over here. All right, we got something. I'm sure I'm doing this wrong, but I think it would be these points here. Because between 0 and 4, positive x. Yeah, so it's this loop here, this part here. Sorry, that would. So something like this, right? Just this and the y-axis. Just this little region here. All right, and that region, right, they're calling that Q. And once again, this is being rotated around the x-axis. And I want to find the volume of the shape that's created, right? It's a 3D figure. All right, so again, if I'm doing shells, make a slice, make a thin little rectangle here, parallel. So here's a little thin rectangle, and that would correspond to some y coordinate, right? And have a thickness of d, we'll call it dy. And then if I rotated this thin rectangle across the x-axis, right, I'd create one of those rolled up pieces of paper, one of those cylindrical shells. And the radius, right, the radius is always going to be the distance from the line of rotation to the edge, right, to the rectangle. And that's just whatever, from here, it's just from the x-axis. So it's just the y coordinate I picked, right? So r radius equals y. And then the height of it is just the length of the rectangle, which again is the x coordinate to the right curve minus the x coordinate to the left curve, which is just 0. So it's just the x coordinate of the right curve, but in terms of y, that's this thing. So yeah, negative half y squared times y minus 4, right, for the height. And we'd be doing this for every y value, from 0 to 4. So my total volume of the shape created, right, when I rotate this region around the x-axis will be the integral from y equals 0 to 4 of the volumes of these shells, which again is the circumference of the shell, so 2 pi r. 2 pi I'll pull out, it's a constant multiple. R is y times the height, right, times negative half y squared times y minus 4, right, there's the height. Circumference times height, and then times thickness, right? The thickness is the thickness of the rectangle in my picture dy. And this is all they want, right? Actually, I think they have the 2 pi inside. I pull it outside, but this is what they want. They just want you to set up the integral that would determine the volume. So going through these options here, the only one that looks any good to me is this fourth option, right? 0 to 4 for the y. And you have, oh, there's no y. Okay, so it's not that. Okay, here we go. I had 2 pi y, then they multiplied the y and the y squared to make y cubed. All right, so it's this one, sorry, third option. 0 to 4, and then 2 pi y, but then times negative 1/2 y squared I had, right? So that'd be negative 1/2 y cubed, then times the y minus 4, right? And then dy, right? This is your circumference times height times thickness. Great. All right, and then again, they got the picture of the region. All right, so mine wasn't perfect. It wasn't a nice like little heap. It had a little more curviness to it, but um, so there's the region. Rotate that around the x-axis just to take a look at 3D shape being created. And I mean, it looks like there's slices taken out of it. This should be a solid figure. And then yeah, then they got the cylindrical shell, that red cylindrical shell in there. But and we found the integral that was set up, the integral to set up to find the volume of it. Great. Some more cylindrical shells, right? Same thing. Looks like the same thing every time for at least the first two objectives. Then I know there's one final objective where they have us compare the disc and washer method to this cylindrical shell method, and they end up giving you the same thing. All right, so sometimes one will be easier than the other. So you can set up both and see which integral you like better. All right, so again, we're given a region and we're rotating this region around the y-axis to create some solid of revolution and finding the volume, right? So I'll set up the integral and actually find the integral. Right. the curves were given. F of x or y equals 2 times the sine of x squared, or sorry, 2x squared, sine of 2x squared, and then plus 2 after that. So it's bounded, this is above, this is the curve on top, and bounded below by the x-axis, and over the interval from 0. All right, so from x equals 0, x equals the square root of 3 pi over 2. All right, the square root of 3 pi over 2. Okay, so when I plug in 0 here, first off, this is a sine function, so it'll be kind of like a wave. You know, squaring everything is just going to kind of, it'll condense the stuff between 0 and 1 radian, and then extend the stuff after 1. So you have a mixture of a compression and stretch horizontally. But remember the value of the sine of something? It's always between, -1 and 1. I'm just gonna, you don't have to write this really, but this value is always going to be between -1 and 1. All right, so if I double this and add 2, double everything, then add 2 to everything, what you're going to see is that we're going to get some curve where the outputs are never negative. Okay, so when I plug in 0, you're going to get 2, and when I plug in this square root of 3 pi over 2, when I square that, that'd be 3 pi over 2. All right, get rid of the square root, and then times 2 would be 3 pi. And the sine of 3 pi, right? The sine of any multiple of pi is 0, so you get 2 again. All right, 2 times 0 plus 2. And then there's going to be some sort of wavy form in here where it'll hit the x-axis at some place. Because there will be some points here where the sine is -1, so you'll get a value of 0. Yeah, so I'll have some sort of wavy curve. The highest it'll get is 4, as I'm seeing. The lowest it'll get is 0. And yeah, it's going to be something that maybe is really tight to begin with, and then comes out here and, whatever. Maybe it hits the x-axis a couple times. Yeah, just something wavy. This isn't a great, this is actually a terrible picture. This is terrible. All right, let me actually go to Desmos. All right, it should be, it shouldn't decrease in amplitude. All right, I messed that up. Right, it should actually keep going up and down and up and down. Like hit 4, hit 0, hit 4, hit 0. And let me go to Desmos and draw a better picture of this, or show you a better picture of this. So here's desmos.com, a free online graphing calculator. And we had, f of x or y equals 2 times the sine of x squared. Then, oh, sorry, 2x squared. Again, I forgot that. And then plus 2. So actually, there's more condensing on the outside. My apologies, I switched that up. There's a lot more condensing outside one, and, less condensing inside one. Whatever. But you see from x equals 0, right, to x equals the square root of 3 pi over 2. So yeah, so you see it does hit the x-axis one time at this point here. So we're looking at this curve actually. Let me just set the x-axis to go from 0 to the square root of 3 pi over 2. The y-axis to go from 0 to 4, right? I said it's going to only go from 0 to 4. All right. So look at this. This is our graph. All right. This area under the curve, right? The curve is the thing on top. All right. So I'll draw a little bit. I'll draw this in my paper, right? So back on the paper. Let's draw that again down here. All right, so let's draw a better picture down here. So from 0 to the square root of 3 pi over 2, we had something like this, right? Again, there was 0, 2, and it ends at something, this 2, and it looks like this. It loops up a bit to hit 4, down a little bit to hit till it hits 0, and then back up to hit 4, and then back down to hit 2. So something like that, right? It looks something like that on my Desmo site. And then here's the region. Right, there's the region, R. I think they were calling it R. It doesn't really matter. So here's region R, right, both these together. And then we're rotating this around the y-axis. So this is gonna create some weird shape. Right? It'll create some like if you've ever seen one of those dog bowls that have like ridges in them, to keep the dog from eating too fast, right? This would create something like this with a couple of ridges and divots. So I rotate this around the y-axis, and I want to find the volume of this shape. So again, if I'm making a shell, I need to take any slice in here that's vertical, right, parallel to my line of rotation, and that'll be at some x value between 0 and the square root of 3 pi over 2. And the thickness I'll call dx. That'll be the thickness of the piece of paper when I rotate. So when I rotate this rectangle around the y-axis, I'm creating a thin piece of rolled up paper. And the radius is this distance here, which is just simply, you can see it's x. And then the height is just from y equals 0 to y equals the curve, in terms of x. So the height is our 2 sine 2x squared plus 2. And now I can find the volume of this one little shell, and then we're going to integrate. We're going to do this for every x value from 0 to the square root of 3 pi over 2, and then find the total volume of the shape created. So the volume of the shape created integral from 0 to the square root 3 pi over 2. And I'm going to time, and then we're adding up all these shell volumes. So again, circumference 2 pi r. So 2 pi x, I pulled the 2 pi out, times the height, right? Circumference of the shell 2 pi r times the height, which we saw was just to the curve, 2 sine 2x squared plus 2, and then times the thickness dx. Right, and let's go through and integrate this. Now I'm going to pull out a 2, right? Notice how both of these inside this factor have a factor of 2. I can factor out 2. So I'm going to pull that out, and I'm also going to distribute the x. No, I'm not going to distribute the x. All right, so I'm going to pull that out. That's 4. So that's 4 pi out here. Integral from 0. So this is again x equals 0 to x equals square root of 3 pi over 2. Sorry about the tightness there. Of x times then I pulled the 2 out of this, so this is just sine of 2x squared plus 1. So now I can see a little u substitution I can make, right? You might remember back to Calc 1, the method of integration was u sub. I'm going to have u be this expression. I don't like the sine of 2x squared, right? That threw me off when I was graphing as well. I had a rough idea as to what the graph would be doing, but I didn't know exactly what it was doing, right? I had to go to Desmos. But I'm going to call this u. I'm going to let u be 2x squared. And then remember, when you replace an expression with x with an expression with a new variable, you also have to get the differential, right? du for that new variable. So then du And the differential of the new variable is simply the derivative of the old one, right, for the old expression, 4x squared, times the differential of the old variable. Sorry, 4x. Jeez. The derivative of 2x squared would be 4x to the first times dx. And then look, over here, I have x dx. In the integral here, there's an x dx. So that x dx, all right, that would be 1/4 of du. And when I make the replacement, I can pull the quarter out and cancel with this 4, right? Because you'll have a quarter as a constant multiple. You can pull that out, and then 4 pi times a quarter will just be pi. And I can also change the limits of integration. So I'm going to do all that. Make these substitutions. So we got this now. So like I said, this x dx, I'm replacing with a quarter du and then pulling the quarter out. So now this is pi out here, not 4 pi. And I'm going to also change, right, the limits of integration. The lower limit was originally x equals 0. Now when x equals 0, in my substitution here, when x is 0, u is 0 as well. So from u equals 0 to u equals 3 pi, right? When the upper limit, when x equals the square root of 3 pi over 2, plug that in here, that'd be 3 pi over 2, and then times 2 would be 3 pi. So now we're just taking the integral from 0 to 3 pi of, and then making my substitutions in here. For the sine of 2x squared, well, that becomes the sine of u, right? U was 2x squared, and then plus 1. And then the x dx, I already replaced it with a quarter du and pulled the quarter out, so that du is still in there, right? And here we go. All right, now we're doing this much simpler looking integral. And so this is pi, and then times, remember these variables, right? I could replace this with any variable I want. P and p dt, m dm. So doing this integral is just like having x dx, even though it's not the same x as originally. So you treat it like normal. Antiderivative of sine of u would be negative cosine u. And then plus the antiderivative of 1 would be, normally x, but here the variable's u, right? So plus u. And we're going from u equals 0 to u equals 3 pi. All right, and when I plug in 3 pi, the cosine of 3 pi is negative 1. So that value would be positive 1, right? The opposite of negative 1. Plus 3 pi. All right, so that's what I get when u is 3 pi. And then we're subtracting from this when u is 0. Now the cosine of 0 was 1. And this would be negative 1. And then plus 0, so I don't need to write plus 0. And then 1 minus negative 1, that'd be 1 plus 1, that'd be 2 plus 3 pi in here. So this is pi times the quantity, 2 plus 3 pi. And if you distribute the pi, right, you'd have pi, 2 pi plus 3 pi squared. There's the volume of the shape, the weird looking dog bowl with the divots in it, right? That would be the volume of the shape created by rotating that region across the y-axis. So still the same setup, even though the graph was funky and I had to use some assistance, but we can still find the volume of that shape created. Right? So it's 2 pi plus 3 pi squared cubic units. Wonderful. And they factor out 2 pi from this, but whatever. All right. Now again, there's the region. All right, we saw it in Desmos a little bit. I drew a rough picture of it on my paper. And then, yeah, look at what happens, when I rotate this region around the y-axis, and, we look at it here. I mean, see, it's like a big bowl shape, you know, but you have these like divots in it, right? There's a clip in the middle and a ring of a hollow ring out here. It's a weird shape, but you can still find the volume of it using cylindrical shells like this. So yet again, another volume using cylindrical shells, volume of a solid of revolution. So once again, I'll draw a rough sketch of this region being described. And if it's like last time where I can't really get a good picture, I'll just look at Desmos as well and see if I can make a better one. Rotate it around the y-axis this time and find the volume. All right, so here the function we're given is f of x equals or y equals 6 times e to the negative x squared. So this is the graph on top. It says bounded above by this graph, bounded below by the x-axis. Right, so y equals 0, and over the interval from x equals 0 to x equals 2. So the x-axis is on the bottom, and then this is always positive. So when x equals 0, I'm going to get 6, right? 0, 6. So e to the 0 is 1, and e to the negative fourth power, right? When x equals 2, that'd be e to the negative fourth. This is some positive value. 6 over e to the fourth, that'll definitely be smaller than 6. So let's say, it's a 6 over e to the fourth here, and there's the value at 2, and there's the value at 0, and it's going to be some exponential type function, e to some power. And we're under this curve, to the x-axis over the interval from 0 to 2. And it may not look exactly like this, but I think it's reasonable enough. All right, and we're rotating this region, right? This region they're calling R, right? There's region R. Rotating around the y-axis to create like a tent, right? A circus tent. If we were to rotate this around the y-axis, you get some sort of like 3D looking circus tent shape. And if I want to find volume using cylindrical shells, I make a shell, parallel to the axis of rotation, right? So here's a thin little rectangle with a thickness. Now this would correspond to some x coordinate, right, between 0 and 2, an x coordinate, and then the thickness we'll call dx. The radius is just x, right? The radius of the shell, when I make the shell with this rectangle, rotate the rectangle around the y-axis, it'll have a radius of whatever x coordinate I chose, right? The distance from the line to the rectangle. And then the height is just the height of the rectangle, which is y equals 0 to y equals 6e to the negative x squared, right? If I want things in terms of x. So that'd just be 6e to the negative x squared. So I got the radius, I got the height in terms of x. I can find the volume of a shell, and then we'll integrate to find the volume of all shells, and therefore the volume of the solid of revolution. So the volume, the integral from x equals 0 to 2 here, of the circumference, right? 2 pi times the radius, right? Radius is x, times, and then, the height, 6 e to the negative x squared dx. Okay. And then this has a constant factor of 6. I can pull that out. So this is 12 pi times the integral from 0 to 2 of, x times e to the negative x squared dx. Now, if you see the antiderivative already, cool. But you could do a u substitution here, right? Instead of e to the negative x squared, maybe call it e to the negative u or e to the u and change your limits. But I already know the antiderivative for this. It's pretty simple, I feel, because like the derivative of x squared is 2x, right? Or the derivative of negative x squared is negative 2x. So I just get e to the negative x squared, times negative half. So it's going to be 12 pi. And then antiderivative of this would be e to the negative x squared, times negative 1/2, right? If I were to differentiate this, I'd have e to the negative x squared, then times negative 2x would be positive x, right? So I get that back. And we're going from x equals 0 to x equals 2, right? So I didn't do any u substitution here. Again, you could have done a u substitution. I just didn't feel like it was necessary. All right, and then If you want, I can pull the negative half out, right? It's a constant multiple, so this is negative 6 pi times, again, I pulled the half out here, the negative half. So e to the negative fourth power minus 1. Because when x is 2, that's the e to the negative fourth. And then when x is 0, this is e to the 0, so minus 1. And I don't like the negative in there, so let's multiply that, put that negative back. So we have 6 pi times 1 minus e to the negative fourth. Right? And now everything's nice and positive, right? So there you go. This would be the volume, right? Cubic units of the 3D shape created by rotating this region around the y-axis. 6 pi times the quantity 1 minus e to the negative fourth. That should be good there. Right. All right, they wrote it some other way, but the way I have it is equivalent. And once again, here's the region, right? Like I said, my region didn't look exactly like that. So this would be more like not a circus tent, but I don't know, a mound, right? Just some rounded mound shape. When I rotate around the y-axis, right? We can see that here. You can see there's like a witch's hat, you know, that's not pointy at the top. Maybe like a Gandalf's hat, a wizard's hat, but less floppy. I don't know. But we got the volume of it. Next, so yet again, finding the volume of the solid of revolution using the method of cylindrical shells. So I'll do the same thing I've been doing for all these problems. Draw the region that's being described, and then, this time though, we're not rotating around the x-axis or the y-axis. We're rotating around a different vertical line, x equals 2. All right, so again, you saw this in earlier examples in this video if you've been watching. When it's not the x-axis or the y-axis, it's just going to shift the radius a little bit. It's just going to change the radius up a little bit. All right, so let me draw this region. All right, so the curves given to me are, f of x equals or y equals 7x minus 7x squared, and they said that the region is bounded above by this curve, so this is the curve on top, below by the x-axis, right, so the x-axis should be on the bottom, and that's it, right? This, if you were to factor this, right, this is 7x times 1 minus x, so this has 0 and 1, right? 0 and 1 as x-intercepts, and it's a parabola opening down. So it would have a vertex when it's the axis of symmetry for the parabola would be a half, right? So something like this. You There's the region being talked about, right? That curve above, x-axis below. And we're rotating this now around the line x equals 2, right? Which is this line here. Right? Vertical line x equals 2. And going around that line. Right? So again, you can see it would be like this mound, but like, it would be like a jello mold, right? With a whole big gaping hole in it, but it'd be like this round jello mold. And then what's the volume of this mold? So yeah, if I want shells, once again, I take a slice, a little thin rectangle here that's parallel to the line we're rotating across. And this would be corresponding to some x coordinate, some x value between 0 and 1. Thickness of the shell would be dx. And then again, I rotate this little rectangle around that line. I create a cylindrical shell. The radius is the distance between the line and the rectangle, which here is 2 minus x, right? We saw something like this earlier. 2 from the, if I go from the y-axis to the line we're rotating around, that's 2 units. And then from the y-axis to the rectangle is x units, so what's left between them is 2 minus x, right? Take those away. So the radius r is 2 minus x, and then the height of this rectangle here is just the y coordinate of the point on this curve on the top here, which is 7, giving me a 7x minus x squared, right? Y to the top minus y to the bottom, but the y at the bottom is 0. So 7x minus 7x squared is the height. And, now I can find the volume of our cylindrical shell, and we'd be making these shells for every value of x from 0 to 1. So the total volume would be the integral from 0 to 1 of the volumes of these shells, which is, again, the circumference of the shell, 2 pi r. So 2 pi I pull out. The radius is in terms of x, it's 2 minus x, times the height, right, times this 7x minus 7x squared. There's your circumference times height times thickness, right? The thickness of the shell is the thickness of this field times dx. Okay, and now we're integrating this. Now, this finally, okay, I'm seeing this is going to be a polynomial. So I'm just going to enter this in Desmos. I've got nice rational limits of integration. I got nice rational coefficients here. So when I integrate this, this will be some rational number, and then I'll just remember to multiply it by 2 pi, right? So I'm going to do this on a calculator real quick, just to save me some time, save me some paper. So in Desmos, right, for an integral, let me get rid of that stuff from an earlier example. For an integral, you just type in int, and a definite integral should show up. And we're doing the integral from 0 to 1, 0 to 1 of 2 minus x times, and then the height there was 7x minus 7x squared, and then times the thickness, right? It's 1.75, and there's a little toggle off to the side here. It'd be 7/4, right? You can change it to a fraction. I know you can't see it, it's off screen, but to the left of the box. 7/4. This integral is 7/4. And then I multiply that by 2 pi, right? The 7 pi over 2 when totally reduced, right? When I multiply, this is 2 pi times, we said this was 7/4, right? And then the 2 goes into 4 twice, so it's 7 pi over 2, or 7 halves pi cubic units, right? Would be the volume of the Jello mold created, when I rotate this region around the line x equals 2. So back in the homework, it's just 7 pi over 2 cubic units. Again, here's the region. We rotate that region around the line. That purple dotted line represents where x equals 2 is, right? And you see the Jello mold, or the you know, the cake with a hole in the middle. I don't know, some sort of thing there with a hole in the middle that has a volume of 7 pi over 2 cubic units. All right, moving on. All right, so this should be the last of these. Now this one's nice, right? We saw some examples like this earlier. I'm just setting up an integral, all right? It's a multiple choice. Just set up the integral. That would give me the volume of the solid of revolution. All right, so once again, like that's for all these. I'm going to draw a picture of the region in question. And then we'll take a slice of it, find radius and height that would correspond to the cylindrical shell, and then integrate. And this is actually a pretty similar one to the last problem. The curves were given. F of x equals, or y equals 3x minus x squared, one curve. The x-axis of the curve. And that's it. this curve here, if you factor x, that's x times 3 minus x, right? So you got 0, 0 is a 0, and then 3 would make it 0 as well. And it'd be a parabola opening down, right? It would have a vertex when x is 1.5 or 3 halves. Yeah, so here's that curve. And it's also bounded by the x-axis, right? So here's the x-axis. So we're talking about this region again, right? This region here. So they're calling this region R. And we're rotating once again about a vertical line, but this time it is the y-axis, right? It has to rotate this around the y-axis. So again, I get some sort of weird jello mold or a mounded hill with a tornado shape cut out of it, or some cyclone cut out of it. I get some three-dimensional figure. Right, so if I'm making shells, right, I want to take a slice, take a little thin rectangle parallel to the line I'm rotating around. That'll correspond to some x coordinate between 0 and 3. And the thickness of this will be the thickness of our piece of paper, our cylindrical shell, dx. And I rotate this rectangle around the y-axis. I create a shell. The radius is just the distance from the line to the rectangle, and that would just be the x coordinate I picked, when I made my slice. And then the height of it, right, is just the distance from the bottom to the top of the rectangle here. So in terms of x, that's, the y coordinate on top minus y coordinate on the bottom. In terms of x, that's 3x minus x squared minus 0. So 3x minus x squared for the height. And now I can determine the volumes of the shells. And we'll be making these shells, right, for every x coordinate from 0 to 3 and adding them up. So the total volume of the solid created is going to be the integral 0 to 3 of the volumes of these shells, which is circumference, right, 2 pi. I think they keep the 2 pi inside, sorry. So 2 pi times the radius, right, times just x, times the height, right, which is this 3x minus x squared, and then times the thickness, right, times dx. And looking at the options that were given, I think they put the x inside here. I think they actually multiply these, make this 3x squared minus x cubed. But that's all they want, just set up the integral. So we have the integral from 0 to 3 of 2 pi, and then times it should be 3x squared minus x cubed. So that's this one here. 3x squared. This was x times 3x minus x squared. Dx. There's the volumes of your shells added up from 0 to 3. Wonderful. Right, so those objectives are done. We've got one more. So I briefly mentioned this before, like this last objective is going to be relating this method, right, this cylindrical shell method, to the method you saw in the previous section, section 2.2, the disc and washer method. All right, so let's get into that. All right, so again, here's the region. Rotate the region around the y-axis, create your little 3D shape, and the volume of that 3D shape, right, was given by this integral. Right. Yeah, so the last objective is compare the different methods for calculating a volume of revolution. So we're going to go over, remember the disk method was, instead of, we're going to make our slices of the region, we're going to create a little thin strip, a thin slice, a thin rectangle that's perpendicular to the line we're rotating across. Create these disks when we rotate. And we've seen this whole video, right? Cylindrical shells, you're making slices that are parallel to the line you're rotating across. So look at this. Select the best method. Find the volume of a solid of revolution generated by revolving a region around the graphs. So what I'm going to do is I'm going to draw this region, just like always. I'm going to set up the integrals, or at least think about how I would set up the integrals. For this first example, I will actually set up the integrals, but after this, I'll probably just, tell you how the integrals would be set up and say, hey, this would be easier than that. But you're trying to determine which integral setup would be easier to calculate. So here's XY axis again, XY plane. The curves we are given. All right, so the region bounded by the graphs of y equals 4x and y equals negative x plus 13 on the x-axis. So y equals 0. All right, so now we're going to probably need to determine where these meet, right? Because these meet, where is 4x equal to, well, we're rotating around the x-axis. Sorry, rotating around the x-axis. I'll point that out. You'll see that when I do the disk method, I need to know where these meet. If I did the shell method, I won't need to know where these meet. All right, because I know this. I know y equals 4x is some line with a slope of 4 going through the origin, right? There's y equals 4x, and y equals negative x plus 13 would have a y-intercept of 13 and a slope of negative 1. So it would come down, it would be going downwards and then hit down here at, 13, right? And then the x-axis is here. So we get this triangle shape, right? Here's the region being talked about right there, right? That's the region bounded by all these curves, these three curves given. Now let me show you when we do shells, and I'm rotating this around, right? So I'd get some sort of, you know, top looking thing, a spinning top kind of shape, right? Triangle, rotate this around. It would look like a top to me, not perfectly, but it's some three-dimensional figure. And I'm trying to find the volume of it. Now, if I'm doing cylindrical shells, like we've been seeing this entire video, I would make a slice this way, thin rectangle that's parallel to the x-axis that we're rotating around. And that would correspond to some y value. No, I guess I do need to know where they meet. Oops. All right, so let's figure out where they meet. So where is 4x equal to negative x plus 13? All right, y equals y, set them equal to each other. So this would be when x equals 13 fifths. Right. So this point where they meet has an x value of 13 fifths. I would add x divided by 5. And then when x is 13 fifths, the y point of this meeting point here would be 4 times 13, which is 52 fifths, right? 52 fifths, right? So yeah, so I'd be picking a y value here between 0 and 52 fifths. And thickness would be dy. The radius of the shell, right? When I create a shell, radius would just be y. And then the height of it, right? The length of this rectangle here, right? H, it would be the x coordinate, right? It would be the x coordinate on the right curve in terms of y. But on the right curve, right, that's y equals negative x plus 13. The x coordinate would be 13 minus y. So it'd be 13 minus y, and then minus, right, it's the x coordinate on the right curve minus the x coordinate on the left curve. And on the left curve, that left curve is y equals 4x, which has x equals, y over 4. So minus y over 4. And when I put those together, all right, 13 minus y over 4, that'd be 13 minus, 5 fourths y, 1 and 1/4 y. And then now I can set up the integral with the radius and height. So the volume, I'll just put V for volume now. Total volume of the 3D shape. I'd be doing this shell stuff for every y coordinate from 0 to 52 fifths. So it'd be the integral from 0 to 52/5 of the volumes of the shells created, by these horizontal little rectangles here. Which again is 2 pi. That's the circumference of the shell. 2 pi r with 2 pi y. Pull the 2 pi out. And then times the height, right? The height, the distance across, right? This would be the height of the shell, which we saw was 13 minus y, and then minus 1/4 y. So 13 minus 5/4 y. 13 minus 5/4 y. And then times the thickness, right? Thickness dy. So this is the integral that would be set up for if I wanted the volume of this by shells. All right. Now notice it is only a single integral. All right. If I were doing disks instead, right, so I did shell blue, I'll do disks in this green color. Oh, maybe that's too close. Maybe I'll do disks in red. All right, so if I did disks instead, find this same volume. Remember, instead of making a rectangle, sorry, this is going to get cluttered here, but instead of making rectangles that are horizontal, I'd be making rectangles that are vertical. I make rectangles, a rectangular slice that's perpendicular to the line of rotation, perpendicular to the x-axis. In fact, let me do this over here. Let me just draw the picture over here. So this was for shells, and I'll draw a smaller picture, but of the same curve, the same region. X, Y, we're rotating around the x. Right. And we got, 0, 0, then this point here, then here's 13, 0, and you got this triangle region. And I said that, this y coordinate here was 52/5, and this x coordinate where they meet, y coordinate where they meet is 52/5, x coordinate where they meet was 13/5, and then you got 0 here. Right? Now, when I want to do disks, right, I'm cutting perpendicular, so I make a rectangle that's vertical, and it's corresponding to some x value here between 0 and 13. And the thickness will be dx. Now, when I create it, this will be a solid disk. Right, when I rotate this, right, it's like a thin coin. Right, this is a solid shape here. There's no hole in it, and we just need the radius of the disk. Right? No height. The height is the thickness. We just need the radius of the disk. Now, look, the radius of the disk is, the height of this rectangle. Right? This here would be the radius of the disk. So do you see how that changes? To the left of 13/5 on the x-axis, the radius is the y coordinate to this curve, which, over here, we'll just say over here, the radius is the y coordinate to that curve, which is 4x. But over here, right, when I create another disk, right, I make another vertical rectangle, thickness dx and whatnot. The radius of the disk, when I spin this around, right, the radius of the disk here would be negative x plus 13. Right, so what I have is one of those compound regions, right, where the radius changes or something changes about the integral I'd have to set up. So if I want the volume here, okay, I'd have to set up two integrals, one for this region to the left of 13/5, and then one for this region to the right of 13/5, and then add them up. So let me set that up. Oh, and yeah, remember the volume of a disk, right, was pi r squared, right? Pi times the radius squared, the area of the circular face, times the thickness, right, times dx or dy. Yeah, so when I'm doing disks, right, the volume of the region would be, first I have an integral from 0 to 13/5, right? I'd be doing this for every x value from 0 to 13, but I'm breaking it up from 0 to 13/5 and then from 13/5 to 13. So from 0 to 13/5, and then times, the volume of these disks, which is pi times the radius squared, right? So the radius in that region will always be 4x, right? So pi times 4x squared times the thickness. And then we're going to add to that the volume of the second region spun around the x-axis, right? The region from 13/5 to 13. So I'm integrating from 13/5 to 13 of the volumes of these disks, right? The disks in this region, which would be, pi r squared, so pi times 13 minus x, or negative x plus 13 squared, and then times the thickness dx. And I'm going to go to Desmos and show you that these are indeed the same value. I will type in both. But when we're doing this by hand, I personally would say that the integral for shells, right, was easier because there was only one of them. With disks, right, there were two integrals I'd have to compute and then add up. Now, this is a bit tricky too, though, because these are just triangles, really. And if you rotate a triangle around and make a solid region, a solid 3D shape, that'll be a cone. So you have a cone here and a cone here kind of put together. And you know the volumes of cones pretty easily, right? The volume of a cone is 1/3 the area of the base times the height. So it would be really easy to find the volume of this region without integrals. But if you had to use shells or disk method, like they're talking about here, right? They're saying you have to use it. I'd say shells was easier because it's only a single integral setup as opposed to two. But let's just double check, right? I want to show you that those indeed are the same values, right? So when I set up the integral for the volume with shells, right, I had 2 pi times the integral from 0, y equals 0 to y equals 52/5. And then the integrand, I had y times 13 minus 5y over 4, or 5/4 y, and then dy, right? So the volume of this thing is 1,472.443. This because that times pi there is not going to be nice and rational. But I get this value for the volume of the solid created. All right. Now let me go and do the sum of those other two integrals, right, when I was doing disk method. So we had pi times, now I'm just going to do pi times the quantity because, both of these integrals had pi in it. So pi times the quantity, and then the first integral was from 0 to 13/5. And the integrand was, 4x to the second power, so 16x squared dx, x, and then plus, and the second integral setup was from 13/5 to 13, up 13, and the integrand there was 13 minus x, or negative x plus 13 squared dx. And close the parentheses. So you see, they're the same value. 1,472.4435327, blah, 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 blah. They are the same volume, just with, different methods. They give you the same thing. Yeah, so after all that, I would say it would be easier to do one integral than two. So I'm going to say method of cylindrical shells. Now I'll see what they feel about this. Yeah, that's correct. Let's see what they say. Yeah, see, they set up two integrals here, whereas it's only one integral, right? Neither of these integrals is particularly bad, particularly difficult, onerous, right? But the shell method requires only one integral, and the integral requires less simplification. We should do the shell method, right? So again, it is a matter of personal preference, but I'd say for the most part, what they're trying to get you to say here is, if you're setting up one integral versus two, one integral will be easier to do. Unless it's a really difficult integral, right? I mean, this is just polynomials here, right? When I pull out the 2y you just have a polynomial, so that's a really easy integral. If it was something insane, but the two integrals up here were easier to do, I'd say those two were easier. But they were all polynomials, so one is easier than two. I hope that makes sense. So moving on. So again, they're asking us which would be the best method. So this time I'll just draw the region and describe how I would set up the integrals, right? And just describe to you. So, maybe I should set them up. You know what? I should set them up. This is supposed to be instructional. So yeah, so let me write out the region. I'll draw a picture. So our curves just said the region bounded by the graph of y equals negative 9x squared plus 9x or 9x minus 9x squared, and the x-axis. And we're rotating around the line y equals negative 20. All right, so I'm going to put that down here. Here's the line, say y equals negative 20. All right, we're rotating around that line. Okay, now this curve here would have an x, has 0, 0, and, 1, 0 as x-intercepts. And it's a parabola opening down. So that's something like this, right? And so there's that curve. This curve's on top. And the x-axis should be on bottom here, right? It's bounded by these two. So here's the region in question. There's, say, R, region R. And I'm rotating this region, you know, around this line way down here. So it's going to be a big 3D shape with a big hole in it, right? Big gap in it. So this time if I do disks, it's actually going to create washers. Remember, washers are just big disks with little disks cut out of them. So I'll do disks first. Well, actually they'll be washers, but again, a washer is just a disk with a disk behind it. So disk slash washers. So I take a slice perpendicular, right? And this will be for, corresponding to, I take a slice perpendicular to the line I'm rotating around. For some x value, have a thickness of dx, and, remember for a washer, washers look like this. When I rotate this thin rectangle around this line, you get again, it's like a coin, a very thin coin, but with a hole in it. Right, and here's the line, in the middle of that hole is the line we're rotating around. And the volume of a washer, right, you have an inner radius, right? You have the radius of the inner circle that's cut out, and you have an outer radius. I'll call them Ri and Ro, or R0, R1. That's the radius of the bigger circle on the face. And remember, the volume of a washer is, the area of the big circle minus the area of the little circle times the thickness, right? It's the area of the face times the thickness, like most of these thin little prisms are, or cylinders are. So it'd be pi times, and then you have the outer radius squared minus the inner radius squared, and then times the thickness, or again, dx or dy. And I want these radii in terms of x. I'll have dx here. Now the inner radius is simple, right? It would be from the line to the bottom of the rectangle here. That'd be from the line to the bottom of the region. So the inner radius, which I'm calling Ri or R1, that's just simply 20 units all the time, right? No matter what x I'm at, the inner radius is 20 units. And the outer radius, right, is, it's, normally we go from the x-axis, right? So it would be this y-coordinate here, right? This y-coordinate in terms of x, which is 9x minus 9x squared, or negative 9x squared plus 9x. So it's that negative 9x squared plus 9x, but then plus 20, right? You still have 20 more added onto that to get to the line of rotation. So it's negative 9x squared plus 9x, plus 20. Right? There's your outer radius. And then we'll be doing this, right, for every single value of x from 0 to 1, creating all these washers, right? So the volume here, when we're doing the disk or washer method, be the integral from 0 to 1, x equals 0 to x equals 1 of, and then, pi was a common factor, pi is a constant multiple here, times the outer radius squared, so this negative 9x squared plus 9x, plus 20 squared, minus the inner radius squared, which is just 20 squared, that's 400. All right, which if I were to multiply this out, 400 constants would go away, that'd be nice. And then times the thickness, right, times the x. All right, so I'm not going to simplify this, right, but this is it. I'd be setting up, one integral here. And it's an integral, this would actually end up just being a polynomial, this integral from 0 to 1, then you multiply the result by pi. So not so bad. Disks and washers wouldn't be too terrible here. All right, now if I were doing, so I'm going to set up the same integral, but for shells, and you'll see it's going to be quite more complicated than what we just did, right? So I'm going to draw the same picture, 0, 1, you got this, sorry, there's the region R, there's y equals, 9x minus 9x squared, negative 9x squared plus 9x. And we're rotating around the line y equals negative 20. So down here, y equals negative 20, rotating around that line. Okay. Now, if I'm doing shell, we're going to take a slice, parallel. Now, if I'm doing parallel slices here, that's going to correspond to some y value from 0 to, I need the y coordinate up here. So I need to know the vertex of this. Now, that would be at a half, right? This is a parabola with an x-intercept at 0, x-intercept at 1. So that would be at a half. And when I plug in a half here, that'd be, so y at a half would be 9 halves minus, and then 9 times a half squared is 9 quarters. Pull the 9 out, half minus a quarter is a quarter. This is 9 quarters. Right? So the top, so I'd be doing this shell stuff for every y coordinate from 0 to 9 quarters. And the thickness is dy, and the radius, right? The radius is the y coordinate that I picked, right? That's this distance here, plus 20. Right, because I'm rotating around this line that's 20 units further than the x-axis. So y plus 20, cool. And then the height, right, the height of our shell, be this distance here, right, the length of the rectangle. There's the h, height. So it's the x coordinate on the right-hand side, but I want it in terms of y, and then the x coordinate on the left-hand side. And then you subtract those. That's the x to the right minus the x to the left. But I need those in terms of y. Now, being that this is a quadratic, I could do this, right? But you'll see it's a little annoying, right? If I have y equals, I'll just do negative, I'll start the way I had it initially, negative 9x squared plus 9x. And if I factor out negative 9, I'm going to complete the square in this because I want to solve this for x. I want to get x in terms of y. Pull the negative 9 out, and then you'd have, x squared minus 1, and then, sorry, pull negative 9, you have x squared minus x. And then I'll complete the square in here. That'd be x squared minus x, and then, half of this is negative half, squared is a quarter, so plus a quarter, minus a quarter, and then distribute the negative 9 back. This is negative 9 times, these three here make the quantity x minus a half squared, and then negative 9 times negative quarter is plus 9 quarters. All right, there you go. And that's equal to y. I get rid of the fraction here, I'll multiply by 4. It'll be 4y equals negative 9 times the quantity Oop, negative 36. Sorry, I multiplied everything by 4. Actually, let me multiply by negative 4. So it's minus 4y positive 36 times x minus a half squared, and then minus 9. And then I would add 9 and divide everything by 36, take the square root, and then add a half, right? It's a lot. So I'd have x minus a half squared equals, 9 minus 4y divided by 36, right? Which is, 1/4 minus 1/9 y, and then I would take the square root of both sides, which gives me a plus or minus. And then I would add a half. Can you see how this is not the good way of going about this? Right? Because look at this is way, way too complicated for what's being asked for. So, and then one of these will give me the right half, and the other one will give me the left half. All right, so this will be the one with the plus. All right, I have a half plus the square root of 1/4 minus 1/9 y. And then this side will be the one with the minus. All right, 1/2, x equals 1/2 minus the square root of 1/4 minus 1/9 y. And then I would subtract those. Right? Now, if I were to subtract these, right, this height then would just be 2 of these square roots of 1/4 minus 1/9 y. Right? That's the height. That's the distance across here, right? If I take the one with the plus and then subtract the one with the minus, right? And so finally, the volume, all right, you can probably already tell, I would rather use discs, right, or washers. But the volume here, right, I'd be doing this cell thing for every y coordinate from 0 to 9/4, right? So the integral from 0 to 9/4 of, and then the volume of a shell was, the circumference of the shell, 2 pi times r. We said r was y plus 20, right, in terms of y, and then times the height, right, which is this 2 times the square root of 1/4 plus 9 plus 1/9 y, right, and then times the thickness dy. Like, that is ugly. That is very ugly. So, and then just to double check, right, I'll put them both in. Why not? I won't do this much work for the last two examples. But yeah, let's enter both these integrals just to make sure they give me the same volume, right? They give me the same value. So my disk or washer integral was the following, right? It was pi times the integral from x, we were going x equals 0, x equals 1 of, and then in the parentheses here I had the quantity, negative 9x squared plus 9x plus 20, that quantity squared, and then minus the inner radius, right? Square was 20 squared, like 400. Close that, dx, right? So I get the volume of the shape created would be 196.97785 cubic units. Now, let me put in this integral I got doing the shell method. Right? That was the washer method. And I should get the same thing. If I did everything correctly, it should be the same. 2 pi times the integral. We're going from 0, y equals 0 to y equals 9/4, right? 9/4. Times, the radius, y plus 20 in terms of y, and then times the square root, or it was 2 times the square root, sorry, 2 times the square root of y over 1/4, not 1 over y, 1/4 plus y over 9, right, 1/9 y. So the parentheses on this, and then dy, right? That's not the same. Did I do incorrectly? All right, so I'm going to pause here and double check my work. Apologies. Okay, I see where I went wrong here. I typed a plus here, right? I wrote down, if you look back on the paper, this is a 1/4 minus. There we go. Minus y over 9. So apologies for that. mistyping things. See, one little sign mistake can make everything go awry. But yeah, now you can see very clearly, right? These do represent the same volume, 196.9778593.8 blah 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 cubic units. But definitely, right, this integral for the washer method, the disk method, is a polynomial. You have an integrand that's a polynomial instead of this ugly thing up here with the big square root. And the way I had to find this also took a while with the solving for x when you had y equals negative 9x squared plus 9x. Yeah, so definitely the easier of the two here would be the disk method. Wonderful. And again, they run through it. Yeah, see, we cannot write y equals negative 9x squared plus 9x as a single function of y. Remember, there was one with the plus, one with the minus. So that caused some difficulty when trying to do it with the shell method. But with the disk method or washer method, much easier. So yet again, so this one's very similar to actually the first example from this objective. If I were to take this is a line going up, this is a line going down, they meet somewhere, and then rotating, and the x-axis on the bottom, you'd have another triangle shape. You'd have another triangle shape rotate around the x-axis. If I were doing disks, so go back and look at example 1, number 1 from this objective. It's the same thing. When I'm doing disks, I'd have to set up two different integrals, right? I have to find out where these meet and set up two different integrals because the curve on top will change after a certain value of x. But with shells, I'd only have to set up one integral to figure out the volume of the solid here. So, and there'll be polynomials because these are just simple linear equations, linear functions. So yeah, so just again, refer back to example 1 from this same objective earlier in the video, and you hopefully can see that it's pretty much the same problem. Just instead of 4, they have 12, and instead of negative x plus 13, they have 2. Yeah. So I'd say shells again. Right? And they run through the pretty much the same explanation as from example number 1 in the video for that objective on determining, compare the different methods for calculating a volume of revolution at number 1. Right, and then this should be the final question here. Yeah, and this is very similar again to example number 2. So I'm just going to say this one out loud without writing anything. So remember example number 2, they had y equals, negative 9x squared plus 9x. And the x was on top, the x-axis was on bottom, and we were rotating around the line y equals negative 20. Yeah, so all that changed here from example number 2 from earlier in the video for this objective. They changed, the numbers. That's it, from 9 to 8 and from 20 to 14. So this will be another one where the disk method's easier, right? Because when I try to do shells, right, and find the length of the rectangle, I need to solve I need to solve this curve here, solve this function. Yes, I need to get x in terms of y. And there's not a nice, I mean, you can still do it, but it's not nice and easy. And there'd be a plus and a minus, right? There'd be one for the right half of the parabola, one for the left half of the parabola. So it'd be more complicated than it's worth. So yeah, definitely the disk method or washer method when you're finding the volume of solid of revolution for this particular example. All right. Yeah, and that should do it. All right. So that's it for this preview of this Newton Alta assignment, section 2.3. And I'm hoping that watching me do these here will help you out when you're working on them on your own. And as I said at the top of the video, please understand that the questions or numbers I saw here, right, the curves that I saw here, won't be exactly the same as what you see when you work on them on your own, but they should be similar enough where watching me do it helps you out. Right. And, thank you very much for watching.